Utrecht University. So we are very happy to have you here. And of course, it would be nice to repeat this occasion, but in person when the times are better. So without spending too much time on introductions, the screen is yours. Please share your screen.
All right, thanks a lot. And now I'm trying to share my screen indeed. Hopefully it will be successful. Yeah, and this is supposed to be my first slide. Do you see it? Can you see it now?
Yes.
Okay. Well, actually it apparently doesn't let me to put it on full screen from this view, which is kind of strange. Let me try another option before this happens. Wait a second, because I'm afraid that maybe the animations will not work, so I will try to share my entire screen instead. Actually, I never used Zoom from this particular laptop before. And okay, let's do it like that. Okay, so now you're supposed to see my full screen, right?
Yes.
Okay, yes. That's right. So thank you very much indeed for attending this talk, and I'm indeed from Utrecht University, Theoretical Physics Research Group, which is a bit strange because I will talk about experiments, experimental physics, or experimental physicist approach to climate-related research topics and planetary atmospheres related research that we are performing in the laboratory that we'll call the von Karman Laboratory for Environmental Flaws. And well, this is where I have done my PhD back then, and this is where I am working right now. And to the best of our knowledge, maybe that's wrong, but to the best of our knowledge, this is the only laboratory in its 1,000-kilometer radius vicinity, which is actually dedicated to the research of the experimental modeling of atmospheric flaws in small-scale laboratory setups. So let's see what we have here. So the idea here would be this: what makes a planet scale? What makes a planet scale? What makes a planet scale 1,000-kilometer flow phenomena special compared to let's say everyday hydrodynamics that we are used to? Well, there are three factors that are very important differences between the let's say so-called how to say engineering type of hydrodynamics and what we call environmental or geophysical hydrodynamics. These are the three key differences. No, not four, just three. We have three key differences. One, that these systems are rotating, and therefore Coriolis Force plays a very important role in forming the flow systems, whether we talk about either the atmosphere or the ocean system. So on our everyday scale, of course, Coriolis Force doesn't really play an important role. It's hardly detectable. However, on the 1,000-kilometer scale, that is, let's say, the scale of a cyclone or anticyclone in the atmosphere like this one, this is, of course, the most important force acting on the system, and it has to be considered. The other thing is that of course, both the oceans and the atmospheres are stratified media, which, of course, mean that as we go higher up, the atmosphere becomes less dense, and it is not that so much well known, but it's also true for the ocean. If we descend deeper, then we see, well, then we experience higher pressure and higher density because of increasing salinity, first and foremost, in the ocean. So it is also a density stratified medium. And the third most important factor that doesn't really show up in our everyday dynamics and hydrodynamics, for example, in the flow field around the car, or something the engineers always investigate, is the shallowness of the system. So if you take a look at this little snapshot here, that shows the troposphere, basically, as seen from space, we can easily conclude that it is shallow indeed. So the characteristic thickness is like a few tens of kilometers, whereas the horizontal extent is like thousands of kilometers. That means that it makes it as shallow as a soap bubble. And of course, from the dynamics point of view, it has a very important conclusion, namely that the flow in the system will be nearly two-dimensional. And two-dimensional flows can be very different from three-dimensional flows in their nature. For example, in the development of turbulence and how turbulence works will be very, very different in 2 dimensions than in 3 dimensions. And essentially, from many aspects, this atmospheric flow system can be considered 2-dimensional. And this is because of the rotation and because of the shallowness together, which we will see later on. Okay, so being physical.
Can I ask?
Yeah, sure, absolutely.
Is there some like simple dimensional analysis that would tell you that 1,000 kilometers is the typical scale for these
yes,
phenomena?
Absolutely indeed. And we will come to that later, but yeah, generally I would say there is a non-dimensional parameter that is called the Rossby number. A Rossby number practically measures the time scale that it takes. So if you have a system with a characteristic length scale of L, and in it you have a flow with a characteristic flow velocity U, then you can get a velocity scale that goes like U over L, which is practically the time scale that you need to cross the domain. And if this time scale is comparable to the length of the day, so to say, so the rotation period of the system, then you can say that on this scale, Coriolis Force, also the rotation effects are very important.
Mm-hmm.
So this is actually a very simple parameter called Rossby number, and the special version of it, thermal Rossby number, is the one that we will see later on. That has to do with these systems, which are the weather-like systems. And being physicists, of course, what we say is we're trying to make minimal models that are as simple as possible, but no simpler than that as a good minimal model. And so what is the good minimal model for the terrestrial atmosphere, which would show weather-like dynamics? Mm-hmm. Well, we need 2 factors to have weather. Of course, we have much more factors than that, but 2 are the most basic factors, of which if you remove one, there will be no such dynamics. But these are the minimal set of factors that are needed to get a weather-like dynamics, which is the rotation of Earth and the temperature gradient. Now, the temperature gradient, with the temperature gradient, I mean the meridional temperature contrast, so the equator to pole temperature contrast. And this is, of course, provided in the Earth system. And you can see it in this tiny little sketch that you can think of it as if there was a cooling wall, maybe a vertical wall around the let's say, in the polar regions, and another vertical wall that is a heating wall closer to the equator, and in between you have this temperature contrast, of course, because this is because of the differences in the incoming solar flux, obviously. But this is what is driving the convection in the system on the large scale. But it would be a very boring convection, as we will see, had we not have the rotation in the system. But since we have the rotation, then it will be a very complicated and hardly predictable system. And so the idea is, let's construct a laboratory model that tries to capture these 2 basic aspects of the system, and let's see how far can we get with such a simplified model. One could argue that this is an oversimplified model, but still, it would be nice to see that how much of this large variety of phenomena that we observe in the atmosphere or the ocean can be captured in a very simplified, simplistic, I would say, laboratory setup like this. So this, what you see here, is a sketch of a laboratory tank, which you can see the dimensions of, which pretty much like a like a pan in the kitchen. So it's really not a big thing. It's a rotating tank filled up with water to a certain height, which is like this large. You can see that the total height of the tank is not much. It's like 135 millimeters, as it say, and it has two coaxial cylinders in it. There is this inner cylinder which is cooled, so it's kept cold by a cooling thermostat, and there is this outer cylindrical rim of the tank that is heated from the outside by another heating thermostat, and in between, in this annular domain, you have the fluid itself, which is water. Of course, one may ask why we can use water when we are trying to claim that we are modeling the atmosphere. Well, obviously, the atmosphere itself can be absolutely considered a non-compressible medium from the sense of geophysical flaws, because the typical flow velocities, typical wind speeds are, of course, much fsmaller than the speed of sound. And as far as the Mach number is much smaller than 1, you can always say that the fluid is incompressible and therefore acts as water. So atmosphere is a fluid in our understanding. So it is perfectly okay to model the Earth system, the atmospheric system, with water in a tank like that. So we have a cooling in the center and heating in the outer rim, and we rotate it. And now if you compare it with this previous sketch, you can understand what we are getting to. So if you would look at the Earth system from the direction of the axis above the North Pole, then what you would see is that in the center there is a cold region, and at the rim you have a heating region, the equatorial regions, and in between you indeed have this annular domain. So this is a kind of a hemisphere of a flat Earth, a flat Earth model basically. But it's absolutely fascinating how much you can capture from the dynamics using this very simplistic model. And of course, this is not our invention. Such models have been in use since the 1950s from the pioneering work of Hyde in the UK and Fultz in the US and their groups. But it's like amazing that up to this day, they provide new scientific results that can be directly applied in the meteorology or planetology, even planet science, as we will see. And so this is how the setup actually looks like. So it's not that nice as in the sketch, as always. And what we have here, it's not really visible, is a co-rotating infrared camera. So what we can get is a temperature field, a surface temperature field of this free water surface that is here. And from that, we can conclude a lot of things. It's important, of course, to emphasize that this temperature field that we get is really a surface temperature, because the penetration depth of the infrared radiation to the water is really like a millimeter or so. So what we see is always surface temperature. Okay, but let's see what is happening in this setup actually. So what is happening, as I mentioned, is a so-called sideways convection. This is how we call it. You have a cooling on one side and heating on the other side, and which means that obviously the water will rise on the heating side because it gets warmer and the density drops, so it goes up, and this opposite thing happens on the cooling side. So we will have a convective cell, which is not like the typical convection which we are familiar with, which is the Rayleigh-Bénard convection, because in the Rayleigh-Bénard convection, obviously, the heating is always happening at the bottom, and the cooling at the top, and we got used to the idea of a critical Rayleigh number or a critical temperature difference below which there is no convection, and you have to reach a certain threshold for the onset of the convection, because we are fighting gravity in this Rayleigh-Bénard setting. But here, when we have a sideways convection, there is no such a thing, if you think about that, because both the heating and both the cooling are happening on the same geopotential level. Therefore, we don't have to fight gravity in this respect. So however small temperature difference you have, you always get a convection in the system. maybe it's very slow, but there is no such a thing as a critical Rayleigh number. And so this is how the flow looks like. Yeah, okay, it started already. So this is a video that we recorded with passive tracers in a system like that without rotation. So it's just a tank, a glass tank apparently, which is transparent with heating on the one side and cooling on the other side. And we have these PIV, particle image velocimetry tracers, which are really tiny micron-sized particles that essentially have very similar density as water, and they act like tracers more or less. And so you can see how the sideways convecting system works. And this is actually kind of similar, if you wish, to the atmospheric convection cell, if we think about the Hadley cell, for example. Or we can also say that it is somehow similar in a qualitative sense to the deep ocean circulation, or the so-called great ocean conveyor, which is the greatest energy and material transport system on the planet. And it really works like that. If you think about that let's say you have the surface currents in the Atlantic Ocean from the equator to the pole, from to the warm to the cold part. You have this northward current, like the Gulf Stream, if you think about that. And there, of course, there is a deep water formation, so they call it, a sinking at the polar regions where the fluid particles density are increased, and therefore they sink to the bottom of the ocean. And this is how the top branches and the deep ocean currents are connected in this conveyor belt. And this is a very simplistic model of that kind of circulation, if you wish. Okay, but so this is practically how it looks like, but this is not that interesting. Of course, it's a very simple thing. But now comes the funny part, when we turn on the rotation. Now, if we turn on the rotation, and therefore we have the Coriolis force. Now, the Coriolis force is acting on a system as it would in the northern hemisphere, which means that we have to rotate our tank counterclockwise this way, like as if we were looking at the Earth from above the North Pole, as I mentioned already. Then what we will see, then the effect of the Coriolis force in the system will always be that it will push the flow to the respective right with respect to its intended direction, so to say. So therefore, instead of this kind of branch that we've seen before, which would be the nice and boring circulation pattern, you will see we will see deviations in the system and the formation of circular patterns, as we can see, because apparently, as visible from this cross product, it's a force that is always acting to the right of the direction of motion, which will force the particles to follow circular trajectories, of course. But with typical, and this is how we get back to the question that I had, the typical velocity scales in the atmosphere, which are the wind speeds, are such that if you calculate this cross product with omega being the angular frequency of Earth, you will get a radius that is like roughly a few hundred kilometers or 1,000 kilometers, which we call the Rossby deformation radius. And the reason why we don't consider the Coriolis force in our everyday life is precisely because this radius is large if we calculate it with the velocities that we experience in our everyday life. So there are these widespread claims, of course, that if you go to the bathroom and see how the water goes down in the sink, you can figure out which hemisphere you are standing at. But of course, it's not really true at all, because these are secondary, or I don't know, third order effects compared to I don't know, everything else in the bathroom. so it's practically impossible to detect in the everyday life, precisely because of this, because the effect is very small. But of course, as I said, on the large scale, it's very important, and that's why we have to rotate or experiment much faster than Earth's rotation if we want to get atmosphere-like dynamics, like for example, like these guys do here in the playground, because we can see that from the co-rotating camera that they indeed have difficulties to pass the ball to each other because of the Coriolis force. But for that, of course, you have to rotate it much faster than the Earth's rotation. So our experiment, we typically rotate the system with 20 rounds per minute. So 1 day in the system lasts for 3 seconds. And using the calculation that we discussed before, this Rossby number, this non-dimensional number, can be set in the system to have very similar values to the atmospheric circulation. If we calculate it with the size of the planet and with the temperature gradient and with the the duration of the day. Okay, so these are practically our control parameters in the setup. We have the angular velocity and the temperature contrast. That's the two things that we can play with once the geometry is fixed. And let's see some planetary analogs. So what do we see in Venus, for example? Now, Venus is well known to have a very slow rotation, and it means that I think, if I'm not mistaken, 1 day on Venus lasts for 243 Earth day or something like that. So this means that really the rotation is very, very slow, and this means that the Coriolis force is practically not relevant. So there is no such deviation from this convective pattern that I mentioned before. So let's say what we would see in such a system. Now, if we would not rotate the tank, then we would see that, or rotate it very slowly, then what we see in the infrared camera would be like this when we have a cold region in the center, and like here, it would rotate like that. So this is how it would look like. Yeah, well, if we rotate it faster and faster and faster, then we will see the emergence of these eddies. Now, this is because of the Coriolis force, and we can see it from the temperature contrast. So first, if you rotate faster, you can see 2 cold eddies, then you can see 3 cold eddies, and then you can see 4 cold eddies. This is like that. And if you rotate it even faster, then you will see even more larger wave numbers, even get up to 5 and 6 and stuff like that. And these things seem to be rather regular. But if you rotate it faster and faster, this regularity vanishes, and you will get a more irregular pattern that we will see later on. But let's compare the basic structures to the planetary atmosphere so far. So this is like Venus, and indeed, if we look at Venus, which is a slowly rotating planet, if you take a look at this image that was taken by the Venus Express spacecraft, you can see from the North Pole view of the Venus. This side is infrared because it's in the dark, obviously. The other part is optical. And so, okay, well, unfortunately, apparently okay, here we are. So this is axially symmetric, so to say, but here, this is the Earth system, and you can see where the analogy lies. So we have this polar vortex in the Earth system, which is actually why we have this crazy weather right now in April. That the boundary of the polar vortex is basically the jet stream area that separates the cold polar air from the warm air of the equatorial regions, and the mid latitudes where we live is right in between the two. And what we see is that because of practically as a consequence of the climate change, that's interesting, as a consequence of the climate change, what we experience is that the equator to pole temperature contrast is decreasing. So the global warming, of course, is taking place, but the warming at the polar regions are, let's say, around 2 times faster than the warming at the equators, or the globe. No, much faster than the warming at the equators, because the equator practically stays the same, but the polar increase of temperature is like 2 times faster than the global average. So this means that the equator to pole temperature contrast is dropping, and because of that, we will see that with decreasing equator to pole temperature contrast, we will have a more meandering wave pattern. So more like that. And this will yield a more variable weather, because what we experience right now, at least here in Hungary, I don't know what is the situation over there, but what we have here is that it's such a bag of cold polar air just reached our latitude, and from one day to the other, we had snowfall and stuff like that right now in April, and this is what is happening. And the reason why people say that it is a more common now with the climate change, that such how to say polar cold in-breaks, that's how they call it, cold in-breaks are more frequent, is because of the decreasing equator to pole temperature contrast, which makes this borderline between the cold air and the warm air much more meandering. And this is what we see here in the experiment as well. Now, this is what we are talking about. Yes, absolutely.
Yeah, so you have a number of bumps, and you show that when you rotate more, the number of bumps increase.
Exactly.
And so on. And if you is there some sort of typical number of bumps for the parameters that we have on Earth, the temperature gradient and the rotation and so on?
Oh, not really, but please wait till the next slide when we saw a phase diagram, and you will see that if you look at this, for example, this is kind of an answer to your question. These are actual data from the Earth. In the top panel, you see aerosol tracking based on satellite data in the southern hemisphere. So this is the southern polar vortex, and you see wind field in the bottom panel. Sorry, I pressed something accidentally. Yeah, sorry. So in the bottom panel, you see this wind field meandering, and well, you can have a typical number that will be something like 7 or 8. Or between 4, well, it also depends on the season, actually. So it's something between, I would say, 4 and 8. But you can also see that these patterns are not that regular. So it's always changing, not that regular as the bumps immediately, because as I said, if we increase the rotation faster and faster, then when we reach a point where the non-dimensional numbers match the atmospheric case, and we will already see then what we see here, which is a video from the lab experiment, that the propagation is already becoming irregular here in the lab as well. So what you see here is my experiment with the cold cylinder in the center and the heated outer rim. And what is happening is that I just inject a little bit of blue dye, food dye actually, that is used for painting candies blue. So the same type of material, which practically has the same density as water. So it's absolutely a passive tracer. And what we inject it like that, and you can immediately see the formation of these meandering eddies, which are not that regular as the bumps we've seen before in the infrared pictures, because this is already in the what we call a geostrophic turbulent regime. And let's get back to that directly. Unfortunately, it doesn't really want to move. So now we have to wait for the next slide to appear. I have no idea why. So what I want to say is that, okay, yeah, this is how it looks like. Such an irregular wave pattern looks like an infrared from the same setup. You can see already that it is, well, in this particular case, it's something, well, sometimes it looks like 3, sometimes it looks like 4, but these wave patterns seems to be pretty much dispersive, which means that the different components propagate at different velocities, so they modulate each other like that. And of course, sometimes it's hard to tell, but this experiment turns out to be very good in modeling, for example, the typical properties of the day-to-day temperature statistics from actual weather stations. So this is pretty amazing that from such a simple experiment, you get temperature records from a fixed point, for example, and you check the time series that you get, the temperature time series, and you will have very, very similar properties in terms of the distributions or in terms of the asymmetries of the number of decreasing or increasing steps in the time series. You will have very similar statistical patterns as the one that you get in the mid-latitude atmosphere. So it turns out to be a very good model in many sense because of hydrodynamical similarity. And what is also a very important conclusion, I would say, is that because of the fast rotation, we will have geostrophic balance, and geostrophic balance is of course weird, but that's a direct conclusion of the Coriolis force, that we have a temperature pattern like that, for example, from a co-rotating camera, and if we put tracers onto it, you will see, like here, this is also a co-rotating camera, but it's a particle image velocimetry. It's a tracker camera that is tracking the particles, which we seed into the water. Then you can see that these patterns are moving exactly along the isobars, which is, of course, weird, but this is what's happening in fast-rotating Coriolis force-dominated systems, that the isobars are not anymore perpendicular to the direction of the flow, but they are parallel. So the fluid parsers, in the case of a fast rotation, move along the isobars or along the isotherms in this particular case. And now, finally, we get to the answer, which is the phase diagram. And if we combine the two important non-dimensional parameters, one of which is a special version of the Rossby number that I mentioned, which we call the thermal Rossby number. Now, the thermal Rossby number, as its name suggests, has the delta T temperature contrast in it, because the wind velocities in the system are set by the temperature contrast, obviously. So if we have a larger temperature contrast, we would have faster winds. And we compare this to practically to the time scale of rotation, and with some dimension analysis, we get to these non-dimensional numbers where D, B, and A are the geometric parameters of the setup. D is the depth, or in our system, or you can say that this is the thickness of the atmosphere. G is the acceleration. Alpha is the thermal expansion coefficient of the medium, either air or water in the experiment. Omega is the angular velocity, and B minus A is practically the horizontal scale. And this is a non-dimensional parameter, and the smaller, typically the smaller this thermal Rossby number is, the more geostrophic turbulent the flow becomes. So the limit case would be Rossby number 0, which would be the geostrophic turbulence. And so the smaller the Rossby number is, the more important Coriolis force is in the system. And there is another parameter which measures the viscous effects. That's why we have kinematic viscosity nu in the denominator. So the importance of the viscous effects compared to the Coriolis force. This is the Taylor number. And this is the regime diagram that we get. And there is this outer domain when we have this flow that is axially symmetrical. Here, in the middle domain, we have the regular waves with the number of bumps, which we can count. And the Martian atmosphere is something like that, the atmosphere of Mars. And the Earth is already here in this blue domain, which we call the geostrophic turbulent regime, which is not that regular anymore. And it's hard to answer the question that how many bumps do we have, because, well, most of cases it looks something like that. Okay, so that's it.
So yeah. This was a theoretical diagram, or was it an experimental?
This is experimental. Well, of course, ED had a theory that practically gives you this diagram since the 1940s, but it is confirmed by experiments as well. For example, what you see here, these are the wave numbers observed in of an experiment. This is purely empirical, but yeah. So this is both. So we think we understand it theoretically as well, but this particular region diagram. This particular plot is actually a result of experiments.
Can't you do a numerical simulation also? It is quite the simple.
Absolutely, yeah. Yes. But it's not simple. So the reason why we do the laboratory experiments is it's very hard to get actually correctly in numerical simulations, because these are in these systems. For example, in the geostrophic turbulent case, there is a very large connection between the different scales. So this is so nonlinear that it's really hard to resolve in a numerical grid. And of course, it is possible, but generally it turns out that it's much faster to run laboratory experiments than numerical simulations. But as we will see, for example, if we want to do the same problem on a sphere, which is of course hard to do in the laboratory, because we have gravity here, then of course we have difficulties, and we have to turn to numerics anyway. But yeah, generally the Earth-like planets are in these domains of this diagram. Venus, as we could see, is axially symmetric. Mars is somewhere here in these regular baroclinic wave pattern. Baroclinic is just a word, so this is the same thing as I mentioned before, this planetary or Rossby waves. And the Earth is already here in this turbulent regime, and with the global warming, with this decreasing equator to pole temperature contrast, we are moving in this direction, so towards the more geostrophic turbulent scenario. And okay, this is what I mentioned, that this is something we can do in the lab, but you can do the same dynamics in the spherical geometry, with spherical boundary conditions, with warming at the equator and cooling at the poles, but on a sphere. And if we have the sphere, that also has a scale selection effect, which is called the Rhine scale. I don't want to go into details, but this is in the same type of regime diagram. This is Taylor number and thermal Rossby number again. You will get states in the sphere-like configuration, which you will not get in our laboratory experiments, which has the jets in it, with different flow directions. And this seems to be very, very familiar, of course, for us, because this is practically the case of Jupiter. Now, in the Jupiter atmosphere, we indeed get to this pattern. And this is how, for example, these laboratory motivated studies or numerical simulations can help planetology, for example, because we can see at which value of the Reynolds and Rossby numbers we expect these type of stripes to appear. And from that, we can go backward and calculate the thickness of the atmosphere that is needed to get this pattern. And so therefore, we could get an estimate from this pattern, and comparing it with the simulations, we could get an estimate to the depth of the Jupiter atmosphere or Jovian atmosphere. And since then, it was confirmed by the messenger spacecraft, the Doppler data, that indeed it was a good estimate from this very simplistic model, based on which we could, through the Rossby number and through the similarity of the wave patterns or these flow patterns that we see. Therefore, we could conclude that the Jupiter atmosphere must be something like 3,000 kilometers thick, and this has since been confirmed. And indeed, this changing zonal wind pattern, which looks like this, is as a consequence of the same dynamics on a sphere. Okay, that's another thing that I want to. I know that I'm starting to run out of time, I guess, but that's also a very important consequence of the fast rotation. So the small Rossby numbers, and it may also have to do with Jupiter. Now, this is the Taylor problem theorem. This is a tank that looks like this, filled up with water, and I put a cork at the bottom, a regular cork from a champagne, actually, that was fixed at the bottom. And but just like here, it doesn't reach up to the surface, obviously, and this whole tank was rotating. And here is my view of a co-rotating camera. And what happened is that we injected some food dye again, but this time it was green. But practically the food dye started to spread on the surface, so it did not sink to the bottom. It was higher up. But look what is happening. They try to avoid the region above the cork, which is absolutely fantastic, as if there was a phantom obstacle reaching up to the top. Although there is no obstacle at all at the particular height where this dye is spreading, but still it goes around it as if there was a cylindrical obstacle. And the question is why? And of course, if we take a look at the equations of motion, it turns out that in the Coriolis Force dominated flow, where in the geostrophic balance, which I said, when the Coriolis Force is trying to balance out the pressure gradient, as a side effect, we will get a two-dimensional flow. And of course, when we stop the rotation, it doesn't stay two-dimensional at all. And this is just maybe related to the case of Jupiter, because everyone to these days, since the 17th century, is very, very fascinated to understand what makes the great red spot so stable. And in the 1970s, first the idea came up that maybe this is because of the Taylor-Proudman theorem, because Jupiter is a fast rotator. Of course, it is a very small Rossby number. And it may well be that there is a bump underneath, which we can't see for some unknown effect, but there may be something there. And practically, the reason why we see such a stable vortex as the great red spot is because of the Taylor-Proudman theorem. So there is something underneath, and the flow goes around it, and that's why it stays there since the 17th century. And probably, of course, it's much, much earlier than that, but it was the first time Cassini, I think, first saw it with his telescope. So
it's a giant champagne cork.
Yeah, deep down, it must be the reason. But of course, yeah, I think this theory is outdated now that we have the messenger, because we would have been able to detect this mass concentration of the champagne cork in the Jupiter, which they didn't. But a few years ago, it was still seemed to be an elegant explanation of what we see. And of course, this two-dimensional pattern, to see these things, we don't necessarily have to go to Jupiter. Just look at this satellite image. This is the well-known von Karman vortex street in the clouds behind this island. But obviously, the island is deep down, and the clouds are high up, and still we could see these nice vortices above it. And of course, there are a lot of things that are ruining this two-dimensionality on Earth, most notably the boundary layer effects. So it is not that common that we actually see in the Earth system a nicely two-dimensional pattern, but in this particular case, we do see it. And really, the winds high up behave as if they were moving around an obstacle, which is because of an island, which is much deeper down. So it's a very interesting conclusion of the fast rotation. And also, this may play a very important role in the reason why we see two-dimensional structures in the stratosphere, like the polar light, because the polar light is essentially just a visualization of the flow in the stratosphere. And in the stratosphere, you have the Taylor-Proudman theorem, of course, and this gives you two-dimensional flows. So it's not a surprise that the aurora borealis also seems to be rather two-dimensional. Now, as a last part of the talk, I would like to say a few words about vortices, which are everywhere, not just on Jupiter, but everywhere. For example, in the ocean as well, which we can nicely model. This is satellite thermographic imagery of the Gulf Stream. This is North America. This is Cape Hatteras over here, and this red warm point they detach, and they can survive from extremely long time intervals, like decades in some cases. So it is just fascinating how coherent and stable these structures are, even without the champagne cork. So this is a different story, but even these are extremely stable. And of course, we can model these also in the laboratory. This is a snapshot from the well-known experiment. This time, the Rossby number was set to be similar to the one of the Gulf Stream, and we were tracking these little eddies that were separating from here, which show quite remarkable dynamics. And in even more simple, but the most important thing that I want to emphasize, which seems to be a general property of vortices, whether they are the Great Red Spot or the eddies in the Gulf Stream, or even tornadoes, is that all these vortices have a material holding property. So nowadays, it's still an active research topic whether how we define what is an outer boundary of a vortex. What do we call a vortex? Of course, just calculating the vorticity of the vector field is of course, we know that this is not a good condition to determine whether something is a vortex or not. So definition of a vortex would be that the boundary of the vortex is the outermost material holding surface that is closed. And we can visualize it in the laboratory with a very, very, very simple experiment. This is a magnetic stirrer, which you can't see it because of the optical distortion. But what is happening is here we have a little magnetic propeller. So just a propeller basically in the bottom of this little tank. And all what we do is just we inject food dye, again, the blue one. And you can see this tornado-like structure that everything is like trapped within this boundary. Out of this, where you get dye, this is diluted very fastly and they are spreading all over because of the shear forces. But there is this no shear domain, which is the boundary of the material holding domain, and this is nicely visible. Looks like a tornado indeed. So I think that's a very general property that these vortices in nature always transport material, and if we would shake this bottle or this laboratory tank or move it away, then, and as we did, then this vortex transports the material with it indeed. So it's very hard to destroy it. We tried it very hard to destroy these structures, but it didn't work because they are very, very stable. So it's really amazing. Here are some snapshots of some material holding vortices, and as a last, really the last one would be my favorite material holding vortex that is in the solar system, which is the polar hexagon of Saturn, which is even larger actually than the Great Red Spot. So it looks like that from the Cassini's image. And if we would put Earth onto the surface of Saturn, then it would show its size. So it's even larger than the Great Red Spot. Great Red Spot is like around the size of the Earth, and this is like 5 Earths or something like that. And it's a fascinating thing. Why does it look like a hexagon? It seems to be like a miracle almost. But no, it's a shear instability, which we are studying right now in the laboratory in a very simple experiment. We have a tank, and we have but the tank is fixed in the laboratory frame, pretty much like in the tornado experiment. But now not a propeller is rotating at the bottom, but a plate, which practically has the same diameter as the tank itself. And with different rotation rates, we see different vortices, but these vortices tend to form polygonal shapes. Like, well, here we see a nice triangular pattern, for example. And this is wave number 4, and we are trying to get up to wave number 6, just our motor is not strong enough, so we have to do something here. But really, the message here is that in the case of Saturn as well, it is happening, like as we can see it already, that because of the different stripes are moving with different velocities, therefore there will be a shear, and because of the shear, there will be a shear instability, and in the shear instability, we have a wave number selection, and because of the periodic boundary conditions, of course, only integer wave numbers can be selected, and if the shear is large enough, we will get nice looking regular structures like this one. This is again another instability. It's not the because of the temperature difference that we've seen before. That's another instability because of shear. But here again, we can see very regular patterns, and we are now working on it, and hopefully we'll publish a paper about that this year. And the idea here is, again, that if we understand the dynamics in a system that is remotely related like this one, and we understand how, for example, the wave number is connected to the typical depth, for example, then we can conclude something that may be applicable to Saturn. For example, we can figure out the thickness of the Saturn's atmosphere, which is not known. So this can be useful. And that was everything that I wanted to present today. And I guess I'm a little bit over time already. So thank you very much for your attention. And of course, if you still have questions, just don't hesitate to ask.
Thank you so much. This is a virtual hand clap. This was a beautiful seminar. Physics can be used in many places, and it's nice to see that we can use it to understand our things we see around us, not just the microscopic things. But I'm sure there are many questions. So I see a hand. Martin, you are.
Yeah, thank you. Thank you for a beautiful talk. Unfortunately, in one crucial moment, I had a phone call when you were explaining why the quark affects the upper layers as well, and you explained it by Coriolis Force. Can you, in one sentence, repeat this, because I missed that? And
yeah, okay.
Go on, and then I have a real question.
Okay, the keyword is Taylor-Proudman theorem, and this is really just very simple. The idea is that if you write down Euler's equation and with only two terms, the pressure gradient and the Coriolis force, and you ignore everything else, and you take the left side to zero, saying that you're searching for an equilibrium solution where nothing moves, and it will turn out that the Coriolis force balances out the pressure gradients, and this is precisely why the things move along the isobars. But because the Coriolis force in the system is depth independent, therefore the solution will also be depth independent, which makes it two-dimensional. And because of this two-dimensionality, it is forced to go around the cork in the bottom. And therefore it has to go around the phantom obstacle at higher layers as well. But yeah. Okay, this is like a hand-waving argument.
No, thank you. I got it. Thank you very much. Yeah. And now the real question, like, does the changing of seasons have any effects, like the tilted axis? Would this change something a lot, like
the change of seasons? You asked. Sorry.
Yes.
Yeah, it does. Yeah, indeed. So for example, this wave number that was asked before, that how many bumps do we observe? This is very closely connected to the Rossby number. Rossby number is connected to the equator to pole temperature difference. Equator to pole temperature difference is naturally connected to seasons. So indeed, in the summer, for example, the equator to pole temperature contrast is not that large as for example, in the what was it called, around the okay, maybe it is. So I think that the maximum of the equator to pole temperature contrast may be when you have the equinox cases. And then probably, but the message is that it is absolutely season dependent, correct? And you can actually see it from the number of bumps that you typically see, which is different from season to season.
Okay, thank you.
Tomasz.
Yes, thank you very much for this really extremely interesting talk. And I would like to ask about the video that you showed at the beginning, when the container was still not rotating yet, and there was the convection there, but it seemed to me that there was some flow that I would not expect. So maybe if you could show it again, then
yes, I'm trying. Just let's see.
And also, was it a view from the side or from the top?
Yes. No. It was from the side. Absolutely.
Yes, yes.
It's from a transparent tank, which is not exactly the same as the one where we performed the rest of the experiment. So it was just a regular rectangular tank, and then trying to show it to you. Of course, it. Okay.
Yes.
Yeah, but
yes, exactly. So I expected on the right-hand side that it would just go up, and at the bottom it would go from left to right. But
and instead you have this other cell, right?
That's right. That's right. Exactly.
Yeah. That's weird. That's weird indeed. It's amazing that you noticed this. Actually, this is a concept, and what you see here is a two-dimensional slice, because we produce these videos with a laser sheet, because these are fluorescent particles actually, and this is how we can visualize a 2D field with a vertical laser plane. And the reason, and to understand that, there is a this is fantastic that you actually realize that you're the first one actually. So the reason for that is that in this particular experiment, because of the limited size of the tank, there was also a flow that was moving in the perpendicular direction of the plane, and this caused some disturbance over there. And this is the reason for that. So you are totally right that if it was indeed an infinite domain in that direction, you would not see that. But it was a closed rectangular box, and it had, and we were heating it from one side and heating from the other side, but the other two sides of it were transparent, and there was no heating nor cooling on those sides, and therefore we had some extra current that was modifying the flow. So you will not get this from a theory. It's just an experimental artifact.
Thank you.
Well, I thank you for noticing it. It's fantastic.
Okay. Any more questions?
I have a question.
Yes.
So we know that on Earth the mountains can experimentally and theoretically only be a certain size. So if we talk about the Cork Mountains on Jupiter, well, I presumably they're not made of cork. How big can mountains be on Jupiter?
Well, I'm not even sure that that's a good question, in the sense that I'm not even sure that there could be any mountains on Jupiter, or whether I'm not even sure that it has a solid surface. But the idea here is that from this Cork idea you can't really determine, because this exactly states that however small, in a really theoretically fast rotating system, however short your cork is, you always get a 2D flow around it. So like if you think about this,
that's ideal. I mean, in
yeah,
practice,
that's ideal.
there must be a limit.
There certainly is a limit, but I'm pretty sure that technically the rule is if it wasn't a gas giant, it would say that the tallest mountains on such a big planet must be shorter than the ones on Earth. So the reasons why we have Olympus Mons on Mars is that can be that large, like 23 or 25 kilometers, depending where you measure it from. It's because Mars has a reduced gravity, and I read it in several papers that such a large mountain would collapse on Earth. So from this, I get that on Jupiter, maybe even Mont Blanc would not survive.
Right. So you're saying that maybe realistically the bump is maybe, you said that the depth was 3,000 kilometers, and
yes,
the bump is maybe only 1 kilometer. Or...
Even that, yes, that's right.
Yeah.
But I still don't know what the bump is. So it is like, it is backwards reasoning. So we know that Jupiter has this depth or an atmospheric thickness, and we know that it rotates that fast. So we know what is the Rossby number, and we know that at such small Rossby numbers, the flow must be roughly two-dimensional. And from that, it follows that there must be something. But it's also possible that this is not the case, that this is just one of those other things that I mentioned, material holding vortices, which can also last very long, and those things don't need a cork. So that's a question that is still open, to the best of my knowledge. And then this is why it's amazing that such simple lab experiments can indeed provide some useful input to these problems, which is almost unbelievable in 2021, but it's true.
So, Tomasz, do you have another other question? Your hand is still raised.
Oh, sorry. I forgot to put it down. But when you ask, then maybe I would still have one, and namely in the phase diagram where you show these regions and the curves that separate like different numbers of these different polygons. So it seemed to me that the number 7 was somehow just small region.
Yeah.
So can you get more than 7 or?
Well, it depends. So this is where you see that although we are trying to say that these Taylor and Rossby numbers are fairly universal non-dimensional parameters, but actually the number of the wave numbers that you can actually observe in the regular regime is pretty much depending on your geometry. And this is what is happening here in reality in these lab experiments. You can see that there is a typical gap width, which we set when defining the inner and the outer radius. Now, what is happening practically is when we are rotating faster and faster, then we are decreasing, for example, the Rossby number, which means that the radii of these little cyclones and anticyclones will get smaller and smaller. And now comes the apparatus part of the story. Now, if the diameter of the vortex is already much smaller than the gap width, then the vortices start to interfere with each other and move freely. So it's a packing problem. How many circles can you pack into that annular domain? And if they are smaller than the annular domain, then you are already find yourself in the irregular regime, because then so this is practically where we did that particular experiment. I think we got this wave number 7 there and only there because we had this and this gap width. But had we applied a different gap width, then probably it would look slightly different. So as far as the numbers are considered, this depends a lot on the experimental geometry, I would say. But as far as the domains are considered, the basic layout of them, and again, I'm talking about order of magnitudes here, so not precise values, but the layout of the phase diagram is always the same. But these tiny little differences are setup dependent. That's right.
Thank you.
So if there are no more questions, I think we should thank Miklos once more for this.
Thank you for having me.
So with that, I end the seminar for today, the scientific part.